Hi guys. Today we're gonna start Unit 4. The first chapter of Unit 4 is chapter 23, talking about our immune system. So this is a functional organ system um, that you didn't get to hear from it from Bio 31 anatomy. So that's why in anatomy we have 11 organ systems, but in physio we extend one more organ system to include immune system, so it becomes now 12 organ system. This is a very interesting organ system in a sense. It protects you from infections. It allows 24/7 protection, for example, detecting cancer cells before it gets out of control. It also, unfortunately, can detect transplanted tissues. This is why, we reject organs that we receive from a donor. So let's say you are a heart recipient, your immune system eventually, ultimately will reject that heart because it recognizes that heart is basically a non-self entity. So it will basically try to get rid of it. Because of this, all organ transplant recipients have to take immunosuppressants, meaning medication that suppresses their immune system, uh, as long as they have that transplanted organ in their system. So, and when we talk about this organ system, the immune system, it has actually two arms. It has two divisions, if you will. So it has the non-specific defense, um, meaning these defenses, you are born with it. And there's another one more complicated, more advanced. It's called specific defense. It's acquired after birth. So the first portion of chapter 23, we're going to talk about non-specific defense, and the second part of the lecture, we're going to cover the more advanced, more um, complicated, the acquired arm of our immune system. So before we start the actual immune system, let me try to, uh, where do I annotate? Okay. So let me begin with here defining some concept of immunity. For example, if you are being susceptible, it means that you lack resistance to a disease, meaning you don't have immunity. You are prone to become sick. So that's why we call being susceptible is lack of resistance to disease. The opposite of the spectrum is the ability to fight off an infection. Oops. So that's, we call it immunity. So ability to fight off an infection here. So ability to fight off, for example, a viral infection, to fight off a bacterial infection, to fight off a fungal infection, to fight off an infection involving parasites, for example, protozoan organisms. These are, so we can be infected by both prokaryotic organism and eukaryotic organism, meaning unicellular organisms from the prokaryote domain of life, or unicellular and multicellular from the domain eukaryote domain of life. And then when we talk about the non-specific defense, you can have here, let me show you. Hello. So over here, let's erase this. So let's talk about the non-specific defense. And under non-specific defense, we have two lines here, the first line and the second line. Okay. So talking about the first line of defense over here, we have three items. The first item providing us protection is our cutaneous membrane or our skin. So intact skin, that would be an example of a first line of defense. The second item is the mucous membranes. Mucous membranes, this is a concept from anatomy. Any body surfaces that are exposed to the outside world, to the external environment, displays a mucous membrane. So there are four organ systems actually displaying mucous membranes. They are all exposed to the outside world. The respiratory tract, the digestive tract, the urinary tract, and the reproductive tract. So those are the four organ systems with body surfaces that are exposed to the external environment. So all four organ systems, the digestive system, the urinary system, the respiratory system, the reproductive system, all four of those display a mucous membrane. And the mucous membranes and their secretions provide us with protections. So they can basically impede entry of pathogenic agents, pathogens causing disease for humans. And the third component is it's called the normal microbiota or normal flora, flora Flora, or microbiota, microbiota. Those concepts should be taught in microbiology. So if you've taken microbiology, this chapter 23 should be review material for you. If not, I'm assuming that you've been taking this chapter the first time, so I'm assuming nobody has any background in the immune system, so you're okay with that too. And then when we talk about the first line of defense, the non-specific also has the second line of defense. The second line of defense comes in when the first line of defense has been breached. Okay, for example, if you have your skin cut open, you have your mucous membrane being teared, okay, then the second line of defense comes in. And the second line of defense has four components. Okay, the first line of defense had three, the second line of defense has four. The first one, we are talking about cells that can kill by phagocytosis. And these cells are called phagocytes. And there are four examples of phagocytes. Phagocytes, Phagocytes. Examples of phagocytes, macrophage, neutrophils, eosinophils, and dendritic cells. So those are the types of phagocytes. Again, macrophage, neutrophils, eosinophils, dendritic cells. The eosinophil is spelled Eosinophils. Neutrophil, Neutrophilis. Dendritic cells, Dendritic, and macrophage, Macrophages. So that's the first component, cells that kill by using phagocytosis. Phagocytosis means cell eating. So these cells can actually eat up an entire bacterial cell. The entire bacterium would be brought in inside, for example, a phagocyte, such as a macrophage. The second component is inflammation. Inflammation is local versus fever. The third component is systemic. So inflammation is a localized response. Fever is a systemic response. Both of them are basically involving increase in temperature to fight off an infection. And the last component, the fourth one, is called antimicrobial substance. Antimicrobial, antimicrobial, antimicrobial substances. So these are proteins that are produced by the host cell that can kill bacteria. So these are really, really fancy. It's a fancy concept. It's a powerful tool potentially for future drug development fighting against bacterial infections. That is a relatively new concept. We're going to come back to that and talk about it later in the lecture. So that's a summary of the first two lines of defense for the non-specific immune response. And the third defense, the third line would be the specific defense here, the second part of the lecture. So this would be an example. This is the third line of defense. So we have three line defense. The first line and the second line belong to the non-specific immune system. The third line of defense belongs to the specific acquired immune system. So that's why here you're seeing immune system, two intrinsic defense systems, right? So non-specific versus specific, providing resistance to disease, providing immunity, allowing us to fight off an infection. So the immune system, the analogy would be our armed forces, providing us protection against invaders, non-self entities that invade us and then causing us harm. It is a functional organ system in the sense we do not have a specific bona fide immune organ, right? We only have cells. And then, for example, the lymphatic system have lymphatic organs. The skeletal system have, bones as organs. Cardiovascular system has a heart as organs. So these are bona fide structural organs that the immune system does not have. Because of this, it doesn't get talked about in anatomy. It's a purely functional organ system. So it has a physiological component to it. That's why we discuss this. We address it in physiology, Bio 32, as opposed to Bio 31. So we have a diverse immune types of cells involved in the immune system. We also have a lot of molecules involved too, for example, cytokines. So chemical messengers used by the immune system called cytokines, CYTOKINES. And the lymphatic system is heavily involved in the immune system as well. So for example, the battlefield to mount an attack would start most of the time is in the lymphatic system, more specifically in lymph nodes. And those lymph nodes are organs belonging to the lymphatic system and not the immune system. Again, the immune system does not possess a bona fide, a true structural standpoint immune organ. And then, so the non-specific defense, the first line of defense, and the second line of defense that we talked up here, right? So this is the first line of defense and the second line of defense. So the first line of defense is also known as a physical barricade. So these are physical barriers that protect us from the external environment. So if that physical barricade, these physical barriers have been breached, then the second line of defense would be mobilized. And ultimately, if you have a third line of defense, it will also be activated, called upon to protect your internal organs from disease. So that's the gist for the lecture. So with that said, let's get the ball rolling. Okay, hello. Why is it not working? Okay, let me get out of the screen here, see if, oh, there you go. Okay, so here are the three examples of the first line of defense: the intact skin, so check that out because you won't see anything. So the first example is the intact skin. So intact cutaneous membrane. So it has keratin, and keratin is a very tough protein right here. And secretion, skin secretion is slightly acidic as well. So down here you can see clearly physical barricade. I'm trying to annotate here, but and when I annotate, you don't see. So let's try again. Can I move? There you go. Okay. So keratin, tough protein. That's why the reason why your nails, fingernails, toenails, and hair are so tough is because they are enriched in keratin. We also have skin secretions that form what is known as the acid mantle that basically impedes growth of microorganism on the surface of our cutaneous membrane. So again, here, that's the word here, physical barricade. So the first line of defense are examples of three types of barricades: the cutaneous membrane, so skin secretion, slightly acidic, pH 3 to pH 5. We also have lysozymes from sweat glands. These lysozymes are enzymes that weaken the external barriers from microorganisms. For example, their cell membrane. And then lastly, the sebum, which is basically coming from your sebaceous gland, containing toxic chemicals. And this sebum is also, interestingly, this is your personal smell. Okay, so each one of us have a particular distinctive smell that belongs to us. This is because of your sebum secretions on the surface of your body. The second component is the mucosae. Mucosae is basically plural for mucosa, and the mucosa is the mucous membrane. So you can say mucous membrane or mucosa, or mucous membranes and mucosae. So they line all open-end organ systems. So for example, the respiratory system, the digestive system, the urinary system, and the reproductive system. So for example, the acidic secretion here at pH 1 and 2, that's from your stomach. So the gastric juice is a digestive juice that has hydrochloric acid in it. It's pH 1 to 2, it can puncture your genes, burn your skin, and go all the way down to your bones. Okay, so this is a very nasty, very acidic conditions. This is how it helps you to digest your food in the stomach. So at this point in the stomach, we no longer call that food. It's called bolus. That is in the process of being turned into chyme. And when those nutrients gets into the small intestine, we call it chyme, C-H-Y-M-E. Bolus, B-O-L-U-S. We also have, in addition to the acidic secretions, we also have, again, lysozymes from our saliva and tears. That's also help for digestion in the case of a saliva. And we also have proteolytic enzymes, meaning enzymes that are specifically cutting, hydrolyzing proteins. Proteo for proteins, lytic means to cut. So these enzymes are specifically cutting proteins. So their target is proteins and they cut, right? So an example of that is, for example, you have amylase. No, I take that back, that's for sugar. Proteolytic enzyme, for example, pepsin, we're gonna talk about it later. Pepsin would be an example. Aminopeptidase is an example. Carboxypeptidase are other examples of enzymes that cut proteins. Aminopeptidase enzyme cuts the protein on the end terminus of the protein, at the beginning of each protein, and carboxypeptidase cuts on the carboxylic end of the protein, at the end of the protein. So we're going to talk about that later when we talk about the digestive system. And then we have the sticky mucus. This sticky mucus is also important because in that mucus, we have the mucus is produced by unicellular gland. Unicellular means one cell, and these unicellular glands are called goblet cell, G-O-B-L-E-T. They're up here, the goblet cells. These are unicellular glands. So they secrete a glycoprotein called mucin. M-U-C-I-N, mucin. It's a glycoprotein, meaning a protein with a sugar group attached. Glyco, G-L-Y-C-O, and the word protein, right? So I'm going to shorten that. So glycoprotein, mucin. And what is important is when you mix mucin with water, the two become what we call mucus. Notice how mucus is spelled here, M-U-C-U-S. This is a noun. When we talk about mucous membrane up here, it's spelled M-U-C-O-U-S. This is because this is used as an adjective versus down here, M-U-C-U-S, that's used as a noun. So different spelling for different contexts here, noun versus adjective, okay? Um, so that mucus allows us to basically prevent microorganisms from spreading around. So because of that, those membranes are called mucosa because they secrete mucus. So again, one more time, organ systems that have body surfaces exposed to the outside world. The respiratory tract from the respiratory system, the digestive tract from the digestive system, the urinary tract from the urinary system, and the reproductive tract from the reproductive system. All these four organ systems display a mucous membrane. So I'm going to move up here so I can use the third component is the normal microbiota. It is also known as normal flora, F-L-O-R-A. Okay. That normal microbiota, normal flora, we have resident microorganisms like resident bacteria, like E. coli, that are naturally living in our large intestine in a symbiotic relationship with the human host. So we provide them shelter, we provide them food, meaning nutrients. In return, they provide us with vitamin K. Vitamin K is important for blood coagulation, right? So that's a symbiotic relationship, meaning both the host and the parasite extract benefit from one another, right? So the E. coli, in this case, the bacteria, extract from the benefit for sheltering and nutrients. In return, they give the host vitamin K. So both are winners in this case. Let me be clear here. As long as these E. coli remain in the large intestine, you are healthy. But if they start to sneak into your small intestine, they can potentially kill you, right? Because it will lead to diarrhea and massively and ultimately dehydration, and it can ultimately kill the human host. So this is important to maintain, to make sure that they are basically restrained, residing in their normal environment, which is in this case, the large intestine. Now, this normal microbiota, the resident microorganism, they live on the surface, our body surface, not only in the mucous membrane, they live on the cutaneous membrane. In fact, we are being outnumbered 10 to 1 by these microorganisms living on our body surfaces, 10 to 1. We have around 10 to the 13 cells, 10 to the exponent 13 cells, but we have 10 to the 14 microorganism living with us. So for every body cell that you have, there are 10 microorganisms, right? So we are being literally being outnumbered by them, living with us in a symbiotic relationship. The reason why they don't cause us disease is because we have a healthy immune system. So our immune system 24/7 keep a leash on these microorganisms. So when we talk about this in microbiology, there are also, these microorganisms are called also opportunistic microorganism, meaning as soon as the host immune system weakens, they take over. The reason why we are disease-free is because our immune system is fighting them off, keep them in line, right? So how are these resident microorganisms protect us from non-resident pathogenic agents, right? So that's why they're called normal microbiota or normal flora. The concept is called microbial antagonism. So meaning our resident bacteria, for example, are fighting off non-resident pathogens. So these are not normally living on our body surfaces, right? So how do they protect us? For example, they outcompete for nutrients. So pathogenic agents are not on familiar turf. So they would have a harder time to getting available nutrients versus the normal microbiota. The normal microbiota also can produce harmful substances that can kill off the non-resident pathogenic agents. They can also alter the local pH and oxygen availability to basically deter or slow down the growth of pathogenic agents. So these are the three ways where resident microorganisms are protecting us. So two specific examples. You have, for example, in the female reproductive tract, the vaginal lining, we have that microbiota protecting the female patient from developing, for example, yeast infection caused by C. albicans. Another example is in our digestive tract. So the E. coli here is protecting us from having a salmonella infections along our digestive tract. So those are the two examples where the normal microbiota is protecting the human host against an invasion of non-resident microorganism that causes disease. In other words, non-resident pathogens, non-resident pathogenic agents. So those are the three components for the first line of defense, the three types of physical barricade. Number one, the intact cutaneous membrane, intact skin. Number two, mucous membranes. Number three, normal flora. I can move on to the next one. System seems to be really slow in responding, or I don't know what I'm doing. There you go. Okay. Now, like I said earlier, so if your first line of defense has been breached, meaning cut open, right? So first barricade breaks down, then the second line of defense will be mobilized. And what is unique about that second line of defense is inflammation. So that's the take-home message here: inflammation, inflammation, inflammation. That's unique to the second line of defense. And what is important to understand here is this is non-specific, right? That's why we call it non-specific. It doesn't matter the nature of the traumatic injury, whether it's a paper cut, a more severe injury like a burn, or a bone fracture. It's always inflammation, 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 inflammation. When you see inflammation on you, it means your first line of defense has been breached. And this is a response to a second line of defense coming from the immune system. Okay? And the function of that inflammation is to mobilize the cellular barricade, mobilizing antimicrobial proteins. Okay. So we talked about earlier about the concept of physical barricade. Now we're introducing a new concept, the cellular barricade. This barrier is provided to us by cells, right? White blood cells. Now the question is, how does the body know that, how does the body recognizes self versus non-self? So pathogens like bacteria, bacterial cells, fungal cells, or viral particles, they have a unique surface cell signatures, meaning they have a unique profile of proteins on their surfaces that are different from the ones on the surface of our human cells, right? So because of this, our immune system can recognize self versus non-self. So on the surface of your cells, we have flags, microscopic tags. They are used as a molecular address. These are glycoproteins and glycolipids. Together, they're called glycocalyx. And these are molecular addresses used by the immune system to allow them to recognize, okay, this is us, this is on our team, these are our teammates, leave them alone. But when they go on to the surface of a bacterial cell, a viral particle, a fungal cell, these proteins, these surface proteins are no longer the same. That's why the immune system can recognize that as non-self. And we're going to come back also to that concept very shortly. But for now, for the time being, this is how pathogenic agents are being recognized, because they display distinct, unique surface protein profile that are different from the human host. Moving on to oops. What is wrong with the system today? Hello? You're testing my patience. Ay, ay, ay. Stop here. Let me try to move out this of my screen here and try to share the screen again. Okay, I think it's better if we do it this way. Talk about this. Let's move on to this one. Okay. So these are examples of Okay, so these are examples of the cellular barricade. So examples are phagocytes, macrophage. So those are direct attacks. So these cells attack directly the pathogenic agents, or indirect attack, meaning they release chemicals and the chemicals will go on to attack the cells. So let's start with the neutrophils. Neutrophils, what is unique about them is they're always the first to arrive at the crime scene. The downside is, even though they are always the first to arrive at the site of tissue injury, the more they kill, the faster they die. So they pay a price through their phagocytic activity. So they kill by phagocytosis. So the more they eat, if you will, the faster they die. So that's the price to pay, the caveat to these neutrophils. However, as they start to die off, there's the arrival of a second type of phagocyte comes into play, the macrophage here on the right-hand side. The macrophage are basically, when they are inside a blood vessel, they are called monocyte. monocytes, monocyte, right? And when they physically leave the vascular bed, they leave the capillary, blood capillary, and they get into the interstitial space at the tissue, at the location of the tissue injury, they become macrophage. These are professional killers. They kill by phagocytosis. Their advantage, they're not being affected by their phagocytic activities. They can go all day killing, right, by phagocytosis. So they're not being affected by their phagocytic activities like the neutrophils. So even though they arrive at the crime scene later than the neutrophils, their big advantage over the neutrophils, they can kill all day long, right? So these are professional killers. So these are the two types of direct attack. So these cells literally eat the entire pathogenic agent, the entire pathogenic organism, the entire bacterium, the entire bacterial cell, the entire fungal cell, the entire, viral particle. So that's what they can do. And we call that cell eating, phagocytosis. The other component, indirect attack, these are done by natural killer cells. These natural killer cells are another example of white blood cells. They are like cops. They basically provide surveillance to the entire body 24/7, looking around for any lurking in the background potential pathogenic agents. And when they recognize them, they release proteins. So one example is called perforins here, causing cytolysis. So they're literally puncturing walls in the cell surface, and the intracellular content leaks out to kill the pathogenic agents. Or granzymes, another type category of proteins that induces the pathogenic cell to die, to commit suicide. And the concept of cells committing suicide is called apoptosis. It's written here, APOPTOSIS. So apoptosis, meaning cell committing suicide. So that's your cellular barricade. So neutrophil, macrophage, natural killer cell. And as we talked earlier in this slide here, so the cellular barricade, we also have antimicrobial proteins, which leads to this slide here. The antimicrobial protein, an example would be a specific type of cytokine. So again, cytokine are chemical messengers used by the immune system, and the different kinds of cytokines. In this case, the specific example of a cytokine called interferon, IFN alpha, IFN beta, and IFN gamma. Over here, you can see literally this side, the left side here, the host cell, the human cell, has been infected by a virus. So this cell is doomed. This cell will die. But it's going to go down fighting, right? In other words, before it dies, it sends out interferons to neighboring cells that have not been infected yet by the virus. So specifically, interferon alpha and interferon beta produced by the human host cell that has been infected by the virus. The cell synthesizes these two types of interferons, releases out. These interferons are acting like a paracrine signaling mechanism, meaning local short distance signaling molecules going on to the next cell, notifying the cell, hey, we have an invader, we have an intruder, we have a virus. So the non-infected cell, the non-infected human cells start to produce antiviral protein. These antiviral proteins has the ability to block viral replication. So when the viral particle comes in trying to infect the non-infected cells, this time the non-infected cell is prepared. They have antiviral proteins, for example, preventing the specific DNA or RNA polymerase, the viral DNA polymerase, for example, from working, from replicating viral DNA. This is how we protect ourselves from viral infections. On top of the interferon alpha and interferon beta, we also have interferon gamma. So the infected cell, the viral infected cell, produce and release this third type of interferon, the interferon gamma. And what the interferon gamma does is it goes and it mobilizes more neutrophils, it mobilizes more macrophages to basically start to neutralizing the pathogenic agents. For example, a bacterial infection in this case, or viruses, viral particles in that case. So that's an example. One category is antimicrobial proteins. The other type of antimicrobial proteins are called complement. The complement system consists of more than 35, changed of what 30 plasma proteins now is now currently sitting at more than 35 soluble plasma proteins, meaning proteins that are basically floating in our blood plasma 24/7. And they have the capability of generating the most powerful positive feedback mechanism in the human body, period. This positive feedback mechanism is more powerful than childbirth. It's more powerful than blood coagulation. It's more powerful than the generation and action potential. So this is a no point of return here. Once that complement is mobilized and started, you cannot stop it, right? This is the most powerful weapon that we have, and that is used toward neutralizing pathogenic agents during an infection. And this, again, we're still in a non-specific defense. So it doesn't matter what type of infection we're talking about, whether it's bacterial infection, viral infection, fungal infection, infection caused by parasite, it's always complement system activation. And there are three pathways for the complement activation system. Let me go in your book and fish out the page, because you're gonna read about it. So the complement system is on page 679, 679, 680, and 681. I want you to read the three pathway, the classical pathway, the lectin pathway, the alternative pathway. The classical pathway is on page 679. The lectin and alternative pathway is on page 680 and 681. Read that and learn it as is from the text. I will explain to you the most important concept of the three. So ultimately, at the end of the day, all three pathways end up activating the single most important plasma protein, complement protein, sorry, called C3. C as Charlie, number 3. And that's, I'm talking about on page 680, figure 23, 8. It says complement pathways, right? So you see clearly there, C3. All three pathways converge upon the activation of C3. Right? Now, once you activate C3, C3 is basically split into two plasma proteins. It splits into C3b on the left side here. C3b will induce what is called opsonization. Opsonization. Opsonization means the immune system have this capability of tagging proteins on the surface of these pathogenic agents, these bacterial cells, right? And these proteins, we're going to talk about them later, called antibodies. So these antibodies would be basically anchoring on the surface of these bacterial cells, for example. And the reason, the objective of opsonization is to make these pathogenic agents more visible to the immune system, to facilitate, for example, phagocytosis. Okay. The C3a on the right side will induce inflammation, will mobilize inflammation, will intensify inflammation. And inflammation's objective is to basically prevent the original infection site from spreading. So they are basically isolating that infection site. They start to clear the cleansing process, meaning picking up debris, pathogenic agents, cleansing the tissue injury site, and then kickstart the repair, tissue repair mechanism. So that's the objective inflammation, right? So that's, and then the C3b is down here. It will induce cytolysis, meaning pore formation. Meaning they're gonna cause the formation of a big, huge pore on the surface of the pathogenic agents, and this intracellular content simply leaks out. And the C3b mobilizes other complement proteins, C5. C5 splits into C5a, like C3a induces inflammation, whereas C5b mobilizes additional proteins, complement proteins, so C6, C7, C8, and C9 to form what is called the MAC, M-A-C. Okay? The MAC stands for membrane activation complex. This is basically producing huge opening here on the surface of the pathogenic agent, the cell of the pathogenic agent, and the intracellular content leaks out to kill that pathogenic agent. So MAC again is membrane attacked complex, MAC. We affectionately call it the MAC attack, right? So the Big Mac attack, MAC, membrane attack complex. And the membrane attack complex consists of the following protein, and this is important. It consists of C5b, C6, C7, and C8, and C9, right? So all of them contribute to form that big MAC, the membrane attack complex. And they insert into the cell membrane of the pathogenic agent. Okay, being a parasite, being a bacterium, and that's how it kills the pathogenic agent. And going back to inflammation here, so the objective of inflammation again is a local effect. So we have the objective to get rid of the pathogenic agents, cleansing dead tissue cells and other debris, and setting the stage for tissue repair. Inflammation is local, systemic is fever is systemic, meaning body-wide. So fever is an example also, a response from the body to fight off an infection. So our hypothalamus is a natural thermostat. It sets the body temperature. So it can basically set body temperature to higher baseline. For example, it releases prostaglandins, prostaglandins, and the idea of fever is to increase metabolism, increase body temperature. And the reason is also, the advantage here is to take away, for example, iron, because iron is required for bacterial growth, right? So there are proteins transporting iron, for example, transferins here, sequestering iron away so that bacteria, for example, have a hard time obtaining iron for their bacterial growth, increasing cytokine activity, for example, increasing interleukin-1 activity. That's another specific type of cytokine, interleukin-1 and interleukin-2. We're going to talk about that later. And producing more interferon here, another type of cytokine. The disadvantage of fever is tachycardia, meaning the heart rate, can increase to abnormal levels. Acidosis, that's dangerous. So pH is below 735. Dehydration, and if the temperature is out of control, 46 degrees Celsius, it becomes fatal. Okay? So fever is it's a cleansing mechanism. So sometimes it's a good thing to become sick, because when you are sick and you have a fever, the fever state is basically a cleansing state. You are cleansing your body wide of pathogenic agents. So truly, there's a saying here, no pain, no gain, is truly the case here. So sometimes it's a good thing to become sick, because you need that cleansing once in a while. So that would complete our non-specific defense mechanism. We're gonna go now switch our focus to the more interesting, the more complicated, the more cerebral, if you will, arm of our immune system. This is acquired immune system. This, in order to have this, you need to be exposed to a pathogenic agent. You need to be exposed to an antigen, okay? This happens only after birth, right? So this already, the third line of defense, the acquired, you can say acquired immune system, you can say adaptive immune system, or you can say specific immune system. So before we talk about this, we need to define what is an antigen. And when we talk about antigen, we can talk about complete antigens and incomplete antigens. The complete antigens, for example, is the entire bacterium, the entire bacterial cell, the entire viral particle, the entire fungus, the entire fungal cell, right? The entire parasite. Incomplete antigen is just smaller bits and pieces of an antigen. So when we have a complete antigen, the complete antigens has two capability, two functionality. It can induce immunogenicity, means it can induce an immune response. Reactivity, it also means it can react with that immune response, right? Whereas an incomplete antigen, also known as a haptens, is inert. It is not being recognized by the immune system. It would not cause us anything because they are too small to be recognized by the immune system. So examples are nucleotides coming from viruses, nucleotides, bacterial nucleotides, viral peptides, bacterial peptides, or hormones. These are small peptides, and hormones are small proteins, too small to be recognized by the immune system. However, the immune system, we talked about this briefly, has the capability of flagging something small to make it bigger, to make it more visible, to become more visible, if you will, to the immune system. This is the basis of allergies. So the hapten, as long as it's not being tagged by the immune system, you are oblivious. You don't have any reactions to it. The problem is the immune system starts to tag antibodies on their surface, and they become visible. They're being attacked by the immune system, and we react to it through allergic reactions. So that's the basis of allergic reactions, is because our immune system is now recognizing incomplete antigens, inert haptens, and they attack it. So we suffer during these attacks, known as allergic reactions. And in order to recognize self versus non-self, so the concept antigens comes back. So on the surface of pathogenic agents, these antigens are different from our own self-antigens, which brings us to the third item down here, self-antigens that we're going to talk about. So these are literally proteins on the surface of our cells that are distinct from the protein on the surface of a virus, the protein on the surface of bacteria, proteins on the surface of fungi, and protein surface of, for example, parasite. Okay. So let's go and talk about this concept here. And this is important, the complete antigen and incomplete antigen. So again, immunogenicity, ability to cause proliferation of T cells. T cells is an example of a white blood cells. B cells is another example of white blood cells. T cells are also known as T lymphocytes. B cells are known as B lymphocytes. Okay. So T cells, that's for T lymphocytes, and antibodies here are produced by B cells. So B cells become plasma cells, and the plasma cell produce antibodies. Complete antigen also have reactivity, ability to react with activated T cells, and ability to react with release antibodies. So when you see antibodies, it means we're dealing with B cells, we're dealing with B lymphocytes. And the concept of antigenic determinants or epitopes. So for example here, on the bottom here of the panel, you have an antigen. Let's say this is a bacterial cells, and these epitopes are surface proteins on that bacterium, right? So you have different types of surface proteins. Each one is a unique epitope, and each one is being recognized by a very specific antibody. So this antibody can only recognize this epitope, and this antibody will not be able to recognize this epitope here, this epitope, this one, and this one. So it only recognizes this one here. So we have 1, 2, 3, 4, 5 epitopes. 1, 2, 3, 4, 5. This antibody here only recognizes the second epitope. It will fail to bind to the first. It will fail to bind to the third. It will fail to bind to the fourth. And it will fail to bind to the fifth. Because each of the other epitopes would be recognized by a different, another type of antibody, right? So what are examples of complete antigens? So example of complete antigen would be the first case, the entire virus. So the entire viral particle. That's one example, complete antigen. The second complete antigen, the entire bacterial cell. the entire bacterium. Okay. The third example, the entire fungal cell, one fungal cell. The fourth example, the entire parasite, the entire cell, parasitic cell. The fifth example, so the first four are non-self entities, pathogenic agents. The fourth example, the next two are unique, okay? The next example is your own cells that have become a cancer cell. That is also an example of complete antigen. So a normal healthy cell now becomes a cancer cell. That is no longer recognized as self. That's a complete antigen. Or the last example, a transplanted cell, right? You are basically receiving, you are a heart recipient, then every single cardiac cells on that heart does not belong to you. So that's also the last example of a transplanted cell being recognized as a complete antigen from the immune system and would be attacked by the immune system. Whereas incomplete antigens, they're called haptens. So they go unnoticed by IS, it means immune system. So we talk about this, nucleotide, peptides, and hormones. So they're harmless until they're being recognized, being tagged. So the first encounter, the allergen is symptom-free. The second encounter induces an allergic reaction. And this is the problem here. We don't know the cause of allergic reactions because that first encounter could have happened like yesterday. It could have happened last week. It could have happened last month. It could have happened last year, right? And then the second encounter can happen like today. So we have no clue to backtrack to trace the source of that allergen. So that's why we don't know what was the cause, but it requires the encounter. This is why it's called acquired. You need to be exposed to that antigen in order for you to mount an attack. In this case, an allergic reaction, right? Okay, so moving on to the self-antigen, and this is a very important slide. Let's start with one of two, self-antigen. Every single cell in your body cells, except antigenic presenting cells, except APCs up here. So every body cell except dendritic cells, every body cell except macrophage, every body cell except activated B cells, they display on their surface class 1 MHC, okay? Major histocompatibility complex. So this class 1 surface glycoproteins consists of a small peptide. They are small peptides, short proteins, only 8 to 9 amino acid long, right? And they are displayed at the surface of all your body cells, except, again, antigen presenting cell, except the dendritic cells, except the macrophage, except the activated B cells. Because these antigen presenting cells displays another type of surface protein that we're going to talk shortly. So these small peptides are produced cut by proteases. So you have your own healthy proteins that are being cut down by protease. And small bits of it, 8 to 9 amino acids of these peptides, would be shipped to the surface and presenting located at the surface of your body cells. So these class 1 MHC would hold these small peptides, your self antigen, on the surface of your body cells. And the immune system comes by and they recognize that as a healthy peptide from a healthy cell, and that cell would be left alone. Okay? That's under the healthy conditions. Now, if that body cell has been infected by viruses, so now you have in that body cell viral protein. So these proteases would cut these viral proteins and ship to the surface. So now the class 1 MHC surface glycoproteins would present on the surface of that body cell viral peptides. Now the immune system knows that cell has been infected by viruses. That cell would be killed. Okay? Another example, if instead of being infected by a virus, that body cell is being infected by a bacterium. So now you have bacterial proteins being cut by the protease, and these bacterial proteins would be shipped at the surface, held into place by the same class 1 MHC surface glycoproteins. The immune cells recognize that, okay, this is non-human peptides, and in fact they're bacterial, so that cell also will be destroyed. A third case, the cell is infected by a fungus. So now you have fungal protein being presented. That body cell, fungal infected body cell, would also be destroyed. Same thing, if the body cell is infected by a parasite, the proteins coming from the parasite would be presenting on the surface of that body cell. That body cell would also be destroyed. So this is how the immune system is basically patrolling, sampling every body cells on the surface. They're looking for that peptide. They're looking for that peptide. And if they don't recognize that small peptide as a human peptide, that cell is doomed. That cell will be targeted and destroyed. Okay? So that's for class 1 major histocompatibility complex. Moving on to class 2. So class 2 MHC surface glycoproteins. This class 2 is only displayed at the surfaces of antigen presenting cell, APC. There are three types of antigen presenting cells. The first one, dendritic cells, macrophage, the second type, and the third type, activated B cells, so activated B lymphocytes. So these three categories of cells, they don't display class 1, they display class 2 surface glycoproteins. These are larger peptides. There are around between 14 to 17 amino acid long. And they're the same concept. They are basically held in place by class 2 surface glycoprotein, and they present, right? So if the macrophage just ate up the entire bacterial cell, so that macrophage would present bacterial protein, bacterial peptide, by using class 2 MHC complex. And they present it to the cell's immune system so that the cell immune system knows we have an infection. Okay? Same thing with dendritic cells, same thing with B lymphocytes. They can basically present these pathogenic peptides to the immune system. So that's the concept between class 1 and class 2 surface protein presenting pathogenic proteins, bacterial proteins, viral proteins, fungal proteins, proteins from parasite, proteins from cancer cells, proteins from transplanted cells. Okay. Now I have to go back to type 1 here. So let's say you have a cancer cell now. So the healthy body cells have become cancer cells. So all your human cells now, human proteins, come from, for example, a protein that is cancerous protein. That cancerous protein would be recognized, presented at the surface of the cancer cell. Immune system recognizes that, okay, this is no longer a self-peptide. That cancer cell would be destroyed. Same thing with transplanted cell. Under class 1 here. So let's say at the heart of the cardiac recipient, the heart recipient, that heart presents its own healthy protein coming from another human being. Even though it's a healthy human being, it does not belong to you. So our immune system recognizes that, okay, this is not us. So that's why it would attack that cardiac cell. That's why we have organ rejection. Even though that heart is healthy, okay, it would be rejected because the cell on that heart does not have the same protein as the rest of your body, because those proteins are belonging to another human being. Okay, moving on to how, talking about the first arm of the acquired immune system. So under the acquired immune system, you have what is called humoral immunity versus cellular immunity. Humoral immunity is mediated by B lymphocytes or B cells. So the B lymphocytes become a plasma cell, and the plasma cell here, plasma C stands for plasma cells, produce and release antibodies, okay? And what is unique about the acquired immune system, it has a memory component. It remembers its foe. The non-specific immune system does not have a memory. It does not remember. But the acquired immune system, both the humoral immunity through B lymphocytes and cellular immunity through T lymphocytes, both of them have memory. Both of them have a memory component. Now this is shown here. So the first exposure to the antigen, it can take you up to a week to 10 days before you can have an effective immune response, because it takes that long to produce all these antibodies. So around a week to 10 days before we have an immune response. And during that time, you are sick. You are really, miserable. Okay? But it takes only one exposure. Once you've done that, once you basically recuperate and you're healthy again, your body remembers, because you have antibodies, plasma cells that are used as memory B cells here for future encounter. So they are floating in your system. And upon the second encounter, the second exposure, oftentimes you don't even show symptoms. You are infected. You have the same bacteria in your system. But since the immune system is so strong and it has memory B cell, within 2 days, you can have a response. And not only that, not only is faster upon the second exposure, look at the 10 days versus 2 days here, and also the intensity is also much more stronger response. So not only you can respond faster, you can have a stronger immune response upon the second or subsequent exposure. And this is the danger here. Even though on the secondary exposure, you're not sick, you don't show symptoms, yet you are infected. This is where the danger comes. You can bring it home, you can pass it on to a newborn baby. So even though your child, your newborn baby or your toddler is not going to school, it's he or she stays home, you blame you or your husband or your wife of passing it on to your child. In fact, you might be the culprit here because you are healthy, yet you've just been infected from work or from school and you brought it home, right? So this is the danger of not having symptoms, yet you can infect other people with a weaker immune response, like newborn babies. The immune system is weakened, or you can infect it to the elderly, which they have the immune system being compromised due to the aging process. So this is the danger here of the power of the memory component is, even though after the first exposure, you don't know whether you're infected or not because you don't show any symptoms, because of that power, because of the memory component that the human immunity has. Same thing with cellular immunity later. Because of the memory component, we can have, we can have the concept of vaccination. So acquired immunity here, you can have naturally acquired or artificially acquired. Naturally acquired through active, meaning the actual infection, you become sick, right? No pain, no gain. So if you are becoming sick, you will have memory. So infection, contact with actual pathogenic agent, you will have memory cells, you have a memory component. So through active, naturally acquired, you have memory. Passive here, even though it's naturally acquired, for example, the mother is passing on antibodies to her infant through milk, or the mother is passing on antibodies through her fetus, through the placenta. So both the fetus and the newborn is protected by antibodies, but the fetus and newborn was not exposed to the actual pathogenic agents. So that's called passive. And in this case, in this type of passive response, the child, the fetus, does not have memory component. So active has a memory component, passive, no memory component. Artificially acquired, through vaccination, you can give to a human being a dead pathogenic agents or a attenuated, a weakened pathogenic agents. So it induces the immune system of the human being, your patient, or the individual that received the vaccine inoculum, to basically produce antibodies, right? So you're training immune system to be ready when, if you encounter the real pathogenic agent, you're basically immune to it. So you are recreating, allowing your immune system to have a secondary response here without the first primary response, because the primary response is the vaccination, the inoculum, containing a weakened pathogenic agent or a dead pathogenic agent. And that you also have a memory component. Artificially acquired, you can also have passive, meaning you can give your patient antibodies, and that's without exposure, so there's no memory component here. So passive means no exposure to antigens, so no memory, whereas active, both of them are exposed to the antigen, so we have a memory component. And when we talk about antibodies, we have 5 classes of antibodies. I would like you to focus, so there are 5 types. Antibody, they're called IgG. So here, uppercase I, lowercase g. So IgG is 1. So the 5 cases are here. So IgM, IgA, IgD, IgG, IgE, right? I would like you to focus on 2 of them. The IgA here, shown here, is basically secreted in mother's milk. So it provides the newborn some protection. So on the passive antibodies into the milk, that type of antibody is IgA. IgG is go across the placenta, it protects the fetus during utero. So antibody from the mother to the fetus through the placenta, that's IgG. So IgG protects the fetus, IgA protects the newborn through milk. That's all I'm asking you to know about. So you need to know the names of the 5 types of antibodies, but the 2 functions specific is IgA and IgG. Okay. And moving on to antigen presenting cells. So we have here dendritic cells, the most effective APCs. So APC stands for antigen presenting cells. They're located in the cutaneous connective tissues and epidermis, macrophage, lymphatic tissues and organs, for example, lymph nodes, connective tissues also, and activated B cells, activated B lymphocytes. And all of these 3 categories of APCs, they use class 2 MHC to present antigenic peptides at their surface. They're not using class 1, they're using class 2. okay? And once they do that, they go and they present that to a helper T cells. The helper T cells is the most important cell of the immune system. They are like a conductor of the orchestra. They can mobilize, they can activate the humoral immunity, they can activate the B cells, they can activate the T cells, the cellular immunity, but they can also intensify the non-specific defense. This is why the HIV, the virus that causes AIDS, is so deadly, is because the HIV targets T cells, helper T cells, right? They neutralize the helper T cells. So if you shut down the helper T cells, you're shutting down the entire acquired immune system. So the patient no longer has that acquired immune system, the more powerful armored immune system. The patient is left with a non-specific defense, which truly, really sucks because a simple cold can kill the patient, right? So because of that, the virus, the HIV, it's so effective in shutting down the acquired immune system because they neutralize the helper T cells. So that's an example here of how it's working. The antigen APC, in this case, a macrophage, picks up an antigen, eats it up, let's say a bacterium, and inside, protease is cut down the bacterial protein, and it displays that bacterial protein through the class 2 MSC, and it presents to the helper T cells. The helper T cell down here, it recognizes it, and then it releases cytokines, specifically interleukin 2. And in this case, interleukin 2 is acting like a paracrine signal, meaning short distance. So interleukin 2 goes on to activate the cellular immunity, the T lymphocytes. It also activates the B cells, the B lymphocytes, to produce memory B cells and plasma cell produce antibodies here. This interleukin 2 activates the most powerful T cell. It's deadly. It's called cytotoxic T cells. This cytotoxic T cell kills any body cell that has been infected by a pathogenic agent, meaning infected by a virus, infected by bacterium, infected by fungus, infected by parasite. Or the body cell becomes a cancerous cell or a transplanted cell. All of those examples would be targeted by the cytotoxic T cells. And they release chemicals to kill the targeted cells. Okay? So we have two components here. Cytotoxic T cell belong to cellular immunity, whereas B cell belong to humoral immunity. So moving on to the last slide. So we have here cytotoxic T cells, and this is important. Going back, let me see if I go to the previous one. If you look at the helper T cells, you have TCR, stands for T cell receptor. That T cell receptor has another surface protein called CD4. So the TCR and CD4 interacts with class 2 MSC and the antigen, the peptide. Okay? We have a same concept for the cytotoxic T cell down here. So you have the cytotoxic T cell, another type of T cell receptor, and now we have CD8 surface protein. So the TCR cytotoxic T cell displays a CD8, and the CD8 interacts with class 1, right? CD4 interacts with class 2, CD8 interacts with class 1 surface protein with the antigen. And once that happens, you will have here again APC presenting or macrophage presenting. So you have helper T cell on one side, cytotoxic T cell on the other side, both of which have a memory component. And so you activate the cellular immunity. So cell-mediated immunity is the same as cellular immunity. It involves T lymphocyte, whereas humoral immunity, here, it involves B lymphocyte, right? So both humoral immunity and cellular immunity, both of them are belonging to the acquired immune system. So those are the two arms of the acquired immune system. Both arms, humoral immunity, cellular immunity, has a memory component. And once you activate the T cells, they are nasty. And this is an example here. The T cells is targeting a cancer cell. This is a former healthy human cells from the host that became cancerous. So they release chemicals. The first one called perforin, we mentioned this earlier briefly. It induces pore formation. This is new. Granulysin, also another protein that can induce also pore formation. Granzymes, these are proteins, protease, that cuts proteins that would induce the cell to commit suicide, so apoptosis. And the most potent of all, called lymphotoxin, it causes DNA fragmentation, meaning it will induce the DNA of the target cell to be fragmented, to be cut into pieces. And whenever a cell that has its own DNA fragmented, cut into pieces, that cell will commit suicide. That cell will commit apoptosis. And on top of that, it's not enough. It also releases gamma interferons. So it elevates the macrophage to killer status. So it mobilizes the non-specific defense into play here. So it amplifies the entire immune response. So that completes the lecture today for chapter 23. And I will see you next time.